So I'm going to go through a few examples just showing how to use the comparison tests for series. So I'm going to go through these 4 examples, and then in all of them I'm going to use the comparison tests. And when I say comparison tests, I'm talking about the direct comparison test or the limit comparison test, which has really like these 3 parts to it. So I have a whole lesson video where I explain like how to use these, and these are just basically more examples on top of that video that I made. So, okay, we're going to start with this first one here. So I've got the sum of 1 plus cosine n over n squared. So a lot of times when you have, so let's say something like this. So just like a single term, I guess. So like n squared, n to the pi, whatever you want. If you just have something like that in the denominator like we do here, that is really just screaming for you to use the direct comparison test, probably. So what do we want to compare this to? Well, okay, if you think about it, so cosine n, that is always going to be a function between 1 and -1. And then if I add 1 to those, so -1 plus 1, and then 1 plus cosine n, and then 1 plus 1, and I divide all of these by n squared. So this kind of builds up a pretty good comparison. And so this equals 2 over n squared. So I would like to make this comparison. This is just 0, so this is not very helpful, but 2 over n squared, so this is going to hopefully make a pretty good comparison. And so if we read over the direct comparison test, so the thing that matters with the direct comparison test, so you're going to have a series a sub n and b sub n. So as far as like which one is which, that really depends on this relationship here. And like you can kind of manipulate this test. So like sometimes you might want to make an a sub n, so make a series that's like less than the one you were given, so that you can prove divergence. Versus in this case, we're going to have this b sub n. So what we've just created, this is hopefully going to show us convergence, because read what this says. So I have this relationship here. So a sub n is less than or equal to b sub n. So then if b sub n converges, then a sub n converges. So the series that I've made, if it converges, then we're good to go. And so the series that I've made now, so this series, so n equals 1 to infinity of 2 over n squared. So this is really just the p series. So I'm allowed to take the 2 out and just rewrite this as 1 over n squared. So this is just a p series where my p is greater than 1, which means that this series, I know without having to do any work, I just know this is now a p series, so this is going to converge. Okay, so since this is the bigger series, then right by the direct comparison test, if the bigger series converges, then the smaller series converges. So this converges. Okay, so let's keep going. Okay, so for my next one, so I've got 1 over the natural log of the natural log of n. So once again here, this is one with kind of like a, we can compare this to a simpler denominator pretty easily. So this is probably a case where I'd want to use the direct comparison test. So the thing to note is that in general, n is greater than the natural log of n. Okay, so you take the natural log of anything versus just that number itself. This relationship holds once we get, remember our n is greater, 3 or greater, so this relationship holds. And if this is true, then it's going to also be true that the natural log of the natural log of n will be smaller. So notice this relationship. I've got n, natural log of n, and then natural log of n. Now, I know this relationship is true. So then, therefore, when I want to set up my comparison, I'm just going to take the reciprocal of all of these. But the big property to remember here, this is like a really standard trick that you use when you're trying to make comparison tests, is that now all of these inequality signs flip. Boom, boom. Okay, so now this is kind of what I was talking about, like with the direct comparison test. So now in this case, the series that I'm comparing to, this is smaller than the one that like my original one that I was given. But in this case, now that it's smaller, so if the smaller one diverges, then the bigger one diverges. So I've set this up in such a way that I can see that this is the smaller one. And I know, right? So I know that this series, this is known as the harmonic series, and it's a type of P series. So this diverges. So this is like one of those really important series that once you've got it, you know that it's going to diverge. So this diverges, and therefore, by the limit comparison test, if the smaller one diverges, then the bigger one diverges. So we have now used that relationship in kind of two different ways. And so this is going to diverge. Okay, so now let's look at another example. Okay, so here's a case now where like my denominator's a little bit more complicated. This like could be a little bit more tricky to set up like a direct comparison with. So in this case, so I've got 2 to the n plus 3 to the n over 3 to the n plus 4 to the n. I think it would be easier to maybe try the limit comparison test. So the limit comparison test says, well, actually I'll show the 3 conditions. So you're going to set up 2 series. So A sub n will always be your original series, and then B sub n will be what you're comparing it to. So you set up this division, and then you see what you get. So, okay, in this case, this one just seems like it's a little trickier. So what I'm going to do is I'm going to choose the dominating terms to kind of dictate everything. So I'm going to basically take the limit as n approaches infinity of my original series, and I'm going to compare that with 3 to the n over 4 to the n. Okay, and so hopefully this will give me something that like is a little easier to work with. So I want to just kind of show what's going on here. So I'm dividing by 3 to the n over 4 to the n. So let's just maybe rewrite that. I'm dividing by 3 to the n over 4 to the n. And when I divide, that's equivalent to multiplying by the reciprocal. So I can do this one more time and rewrite this as 4 to the n over 3 to the n. Okay. And so now I am allowed to multiply these things together because they all have the same exponent. So since they all have the same exponent, I can multiply everything together. So this will turn into then, so let's, 2 times 4 is going to give me 8 to the n. 3 times 4 is going to give me 12 to the n. This will give me 9 to the n and 12 to the n. Okay, so now can I easily find this limit? So I can, if I divide everything, so let's see, I want to divide everything by 1 over 12 to the n on top and on bottom. And so what's that going to do? That's going to turn these 12 to the n's into a 1. So let's clear a little space. Okay, so now this becomes 8 over 12, all of that to the n. This will just be 1, because 12 over n is 1. This is 9 over 12 to the n, and then this is 1. Okay, so this I can much more easily take the limit of now. So since these are both fractions less than 1, as n goes to infinity, both of these are going to end up going to 0. So what I'm left with then is 0 plus 1 over 0 plus 1. So this just ultimately equals 1. Okay, so what do I do with that? So going back to the limit comparison test. So you set up this test and you see what you get. And in this case, I got a number C. So what that means is that either both series converge or both series diverge. Okay, so now let's think back to what I was actually comparing this to. So I'll maybe write that over here. So remember, I was comparing to the series 3 over 4 to the n, or I could write that as 3 to the n over 4 to the n. So these two things are equivalent. So the thing about this is that, let's see, maybe I'll get rid of this for a second and I'll just write it out as a series. Okay, so the thing about this series, 3 over 4 to the n, this is a nice one to compare to because I know that this is geometric. And since it's geometric and it's a fraction less than 1, this will converge. So this was a great choice because this is something that converges, and now I can say that this converges. And so by taking the limit and then finding that I got this once and knowing that this converges, now I can definitely say, so this also converges. And so then again, just notice, like in this case, to kind of help me get through this, I made an easier series that was made from the dominating terms in the original series. So that really helped us out quite a bit. Okay, so for this last one, so now, so I guess my question is to you, what looks better? Does it look better to use the direct comparison test or the limit comparison test? Well, in this case, right, we just have this nice simple denominator. So this is going to actually be a great one for the limit comparison test. And so the thing to know about inverse secant is really bounded by, so it's always less than pi over 2. So if I know that, then I can pretty easily create a little comparison and just divide both sides by n to the 2.3. So I know n to the 2.3, it looks like something really weird, right? But like, as far as thinking about this little series here, this over, so I am allowed, so pi over 2 is just a constant for that series, right? So I can just rewrite this series as 1 over n to the 2.3. So this is once again going to be a p series, and we have that my exponent is greater than 1, and so this is going to converge. So now I've got this relationship here, and remember, if I just go back to the direct comparison test one more time, so the larger series we know converges, therefore the smaller series will converge. That's the relationship that I just maintained, and so now I can say that this converges. Okay. So that brings me to the end of this video. If that was helpful, please consider hitting the like button. Feel free to leave a comment or share this with a friend or subscribe to the channel. And I will catch you guys in another video. Thanks for watching.